A 750 kilogram satellite is located 4 times 10 to the 9th meters from the center of Jupiter. And that's good because that's how Kepler's laws work, right? Got to be between the centers of the objects. The mass of Jupiter is 1.9 times 10 to the 27th kilogram, and this is obviously not to scale, or that would be one gigantic satellite. Determine the force of gravity acting on the satellite due to Jupiter. Calculate the magnitude and describe the direction. Then, determine the force of gravity acting on Jupiter due to the satellite. Calculate the magnitude and describe the direction. On the diagram, indicate the direction the satellite would accelerate if released. We're assuming, in that case, somehow we put it up there with no velocity at all. We just stuck it up in space. Label that vector A. Then calculate the acceleration that that satellite would experience in the unlikely way that we just stuck it up there. Now, instead of letting the satellite fall by somehow just sticking it up there with no other velocity, it was in a stable orbit. Indicate on the diagram a possible direction of its velocity. Label that vector V. Then calculate the velocity that the satellite needs to be in that stable orbit. And finally, calculate the period of the satellite orbiting Jupiter. Determine the force of gravity acting on the satellite due to Jupiter. So, we start with the law of universal gravitation. We plug in big G. Here's the mass of Jupiter. Here's our satellite. And here's our orbital distance squared. We're going to go old school. We're going to split up these exponents into the powers of 10 over here and something which I think I remember being called the mantissa back when we used to use slide rules. So, for example, 6.67 times 10 to the minus 11th, here's the 6.67, here's the 10 to the minus 11th, okay? Then we multiply everything on the left without worrying about exponents, and you get 594. Then on the right side, we just have to multiply those powers of 10. So when you multiply, you add, so that's minus 11 plus 27. And when you divide, what do? You subtract it. There we go. So you're going to subtract 18. You do that, and you get 10 to the minus 2. So you have 594 times 10 to the minus 2 newtons, or 5.94 newtons. Now, what's the direction of that force? Well, Jupiter will be attracting the satellite. Okay, so the direction is to the left, and the magnitude of the force, the gravitational force, is 5.94 newtons. Now, what's the force of gravity acting on Jupiter due to the satellite? Well, we go over to another law created by Newton to describe the universe, not the law of gravitation, but the third law. For every force, there's an equal and opposite force, or equal force in the opposite direction. So the force on Jupiter will also be 5.94 newtons, but it'll be in the opposite direction. The satellite is actually attracting Jupiter. Part C. Label the direction the satellite would accelerate if it was just put there with no tangential velocity or any kind of velocity at all. Well, the force is in this direction, so the acceleration will be in this direction. So eventually the satellite would just smack into Jupiter because it has no other velocity. Okay, so it would just be attracted and hit Jupiter. Calculate the acceleration the satellite would experience. So we can use this equation here, which gives us the gravitational acceleration of an object that is a distance r from the center of Jupiter and the mass of Jupiter. So we plug in universal gravitational constant. Here's the mass of Jupiter. Make sure you use that. It's Jupiter's gravitational field, not the satellite's that we're dealing with. The satellite's gravitational field is just so minuscule we don't worry about it. We divide through by the orbital radius, and we do the same trick we did earlier, where you simplify the calculator by taking all the numbers in front of the exponents, putting them here, multiplying them together. Here's your powers of 10, and you add the powers of 10 in the numerator, subtracted from the denominator, and the final answer will be 7.92 times 10 to the minus 3 meters per second squared. What's cool about this is we can use another one of Newton's equations to get the same answer. We have Newton's second. And what's the only force acting on the satellite? Well, the gravitational force due to Jupiter. So we solve for A by dividing both sides by m. Here's the gravitational force that we already calculated. Here is the mass of the satellite this time because we're interested in the satellite's acceleration, so we use its mass. And look at this, same exact answer. Pretty neat. This time we don't want the satellite to crash into the Earth. That would be a pretty silly thing to do. We want it in a stable orbit, which means we'll call it a circular orbit here. Okay, we want it to go around in a circle so it stays there forever and ever. So what do we need to have that? We want to be in circular motion. We want it to keep the same speed so we can track it. So that's uniform circular motion. That means that the velocity has to be perpendicular to the acceleration vector. We've already said the acceleration is pointed exactly from the satellite to Jupiter, so the velocity has to be perpendicular to that. So we have two choices. You can either make it go that way, give it an initial velocity in that direction, or this way. Both answers would be correct. Now let's calculate the velocity the satellite needs to be in a stable orbit. Well, we have this equation here where the velocity of a stable orbit is the square root of g times m, where big M, that once again is the mass of Jupiter or what you're orbiting, divided by r, which is your orbital radius. We put in our numbers here, and by the way, there's two ways to do this problem, so we'll do this way first. Once again, we've separated out the numbers from the exponents, so hopefully that's a little fun. Or you can just go ahead and grind it through the calculator. Not as cool. And this time we get a velocity is equal to 3.17 times 10 to the 7th, and we need the square root of that. It's hard to take the square root of that 7 and make it 3.5 or something. It doesn't work as well. So what we want to do is get that to be an even number. So how do we get that? Well, there's a little handy phrase. If you move the decimal to the left, it increases the exponent. If you move it to the right, it decreases. The mnemonic is actually decimal to the left increases the power. Decimal to the left increases the power. In this case, we're going to move it to the right, so we get 31.7, and you decrease the power, so it will go from 7 to 6, and now we're good. Square root of 31.7 is 5.63, and the square root of 10 to the 6th is 10 to the 3rd. And at this point you might be saying, why are you bothering with us? We just go ahead and use the calculator. Well, this is how people used to do it back in the days of slide rules, and it's good to know history sometimes. Here's the other way, and it's much simpler. Start with the equation for centripetal acceleration, because we want the satellite moving in a circle for a stable orbit. So you have A is v squared over r. Cross multiply halfway here, so you get AR is v squared. Switch them around, take the square root. Velocity is the square root of AR. Here's your acceleration. Here's your orbit. You have the square root here, and you get 5.63 times 10 to the 3rd meters per second. Same exact answer. We'd like to calculate the period of the satellite. Once again, there'll be two ways to do it. First, let's use Kepler's third law, and we want the period, so we'll multiply both sides by r cubed, and then take the square root, right, because this is t squared. So you get t is equal to 4 pi squared r cubed divided by gm. What we're going to do here is just go ahead and take the square root of 4 pi squared out, put it out in the front. The square root of 4 pi squared is 2 pi. Just makes the math a little easier. So we now have the period is 2 pi. Here's our orbital radius cubed. Don't forget the 3 there. Universal gravitational constant. This once again is the mass of Jupiter. We get a period of 4.47 times 10 to the 6th. Another way of doing it is using one of my favorite equations. Why? Because it's so simple if you look at it not even closely. What's velocity or speed equal to? Well, distance over time. That's one of the first things you learned in physics. If you're going around in a circle, okay, and let's say the circle's radius r, and you make one complete revolution, okay, how far have you gone? Well, that's the circumference of a circle, which is 2 pi r. So that's that. And how long does it take you to do that? Well, that's defined as one period, capital T. So I just love that. Okay, that's cool. We want to solve for period. Okay, so we just multiply both sides by t, comes out all by itself on the left side, and divide both sides by v. So we kind of took a shortcut there. So we have 2 pi r over v. Plug in the numbers. We have 2 pi. We were given the radius. We solve for the velocity in part f. and we get the same answer. And once again, if we want to, well, not once again, but if you want to convert to days, all right, you would do this. You would divide by 3,600 seconds per hour and then by 24 hours a day, and you'd get about 52 days. Kepler's third law problem without mass. 3 satellites, X, Y, and Z, orbit a hypothetical planet. Satellite X has an orbital period of 51 days. The orbital radius of satellite X is twice that of Y. The orbital period of Z is 102 days. What is the orbital period of Y? And what is the orbital radius of Z compared to that of X? What is the orbital period of Y? Since both satellites orbit the same planet, set the period-radius ratios equal to each other. We have the period squared over the radius cubed, and you can see we have X on the left side, Y on the right side. Rx is twice Ry. Okay, so Rx is equal to twice Ry. So wherever you see Rx, put in 2R sub y. Then it's just a matter of cross multiplying, and we get tx squared ry cubed equals ty squared, 2r the quantity cubed for y, right? There's y. So what happens next? What can we cancel out? The ry's cubed will cancel out. So we have tx squared equals 8ty squared. Ty then is equal to tx over the square root of 8. And finally, at the very end, we put in our number. We have the period for x, which is 51 days. Divide that by radical 8, and we get 18 days for the period of y. What is the orbital radius of z compared to that of x? Once again, both satellites orbit the same planet, so we will set the period-radius ratios equal to each other. The next thing we do is the orbital period of z is twice that of x. So tz is equal to 2 times t sub x. And we make that substitution right here. And you can see when we square this over here, we'll have a tx squared on both sides, and they'll be canceling out shortly. So we cross multiply. Nobody likes dealing with fractions. And we have tx squared rz cubed equals the quantity 2tx squared rx cubed. So here's where the tx squares go out. And we have rz cubed equals 4rx cubed. Rz will then be the cube root of 4x cubed. The cube root of x cubed of rx cubed, of course, is just rx. So Rz is 1.6 times Rx. The orbital radius of planet Z is 1.6 times that of the orbital radius of X.